Okay, so in the last class, we looked at this concept of shattering and VC dimension. Recall that we say that a hypothesis class shatters a finite set if the restriction of the hypothesis class to that particular finite set turns out to be the set of all functions from the set to 0, 1, right? And then using that, we defined the VC dimension. So I'd like to point out that I made a mistake in the last class when defining the VC dimension. So let's do it properly once again. So the VC dimension is essentially the size of the largest subset of X, which is shattered by X, right? Which means that the VC dimension is equal to D if for all m less than or equal to D. So essentially every so for all m less than or equal to D, there is at least one set of size m which is shattered by H, right? It doesn't mean that all sets of size less than or equal to D have to be shattered by H. There should be at least one set of size D which is shattered by H. But for m greater than D, no set of size larger than D is shattered by H. Right, so it was kind of a reverse. So it's not all sets that are of size less than or equal to D shattered by H. It is that all sets of size greater than D are not shattered by H. Okay, so that's just please correct that. Uniform convergence, okay. Yeah. So essentially for uniform convergence, a particular hypothesis class satisfies the uniform convergence property if so loosely speaking, something satisfies the uniform convergence property if the empirical risk is close to the generalization error for all the hypotheses in your hypothesis class.
Wondering if that was like for every H,
so this should be for every single H. We want the empirical risk to be close to the generalization. Okay, it's not for some H, it's for every single H in your hypothesis case.
Because I saw a definition where it said like it is kind of like originally negative. So it was like the probability that the empirical risk is more than the generalization risk by epsilon. No, sorry, it was like the probability that the difference between the two risks is less than epsilon. It's always greater than or equal to 1 minus delta for like every H.
Sorry, can you repeat? You want to say that the probability that Rs of H minus the generalization error is greater than or equal to epsilon. Sure. So we want, so it satisfies the uniform convergence property if this holds true for all H in H. Right? Yeah. And this happens with high probability. Correct. Yeah. But so, that's
when you're here.
Correct.
Like so it becomes like for at least one H.
Correct, that's true. Yeah, so essentially for any H in H or for some H in H, they're the same, right? So if this happens, so if this happens for at least one H, then it does not satisfy the uniform convergence property, right? Right. So yeah, so this is sort of a negative statement. If you're looking at the negative statement, then this should happen for at least one H. But if you're looking at the positive statement, then you want this to happen for all H in the hypothesis class.
Okay. So
Yeah.
by any you meant like at least.
At least one, yes.
Because like usually by for any we mean like for every.
No, for any is different from for every. For any means for at least one. For every means it has to happen for every single item in the set. So we want one of these two. Right? Questions? Okay, going back to the definition of the VC dimension. So the VC dimension is the size of the largest subset of X which is shattered by X, which is shattered by H. So let's again just do a couple of examples. We won't go through all of them, but let's take the very simple example of a single threshold. H of X is equal to 1 if X is greater than or equal to alpha, and it's equal to 0 otherwise. Right? So in this case, so firstly, what is this? So if I take M equal to 1, then of course I can generate both choices, 0 or 1. What about M equal to 2? You take any 2 points, right? You take any 2 points, it's impossible to generate all possible combinations, because if let us say x1 is less than x2, then you can't have x1 to be equal to 1 and then x2 to be equal to 0. Right? So that's fine. But let's go to the example of hyperplanes or linear classifiers, as we call them. Right? So once again, what we need to show is that all sets, or for every m less than or equal to d, there exists at least one set which is shattered by H. Correct.
Take the size of the time.
Okay.
Then there exists one structure we can draw the line.
I'm not sure what you mean. In this particular case, you mean this example? What about it? So here X is a real number, right? So H is from R to 0, 1. So what do you mean by collinear? Correct.
And we are saying that there exists
one set X.
one set.
Okay.
That is point.
In which case, can you find a set of size 2 for which is shattered by H? Any set.
Transpose X.
Yeah, we'll get to that in just a minute. Are you talking about that example, or are you talking about this particular example? The one where H is from R to 0, 1. Okay. What is the question? This is R to 0, 1, right? So this is fine, right? Yeah. Let's go to this once again. Right. So now we're dealing with hyperplanes, right? Hyperplane classifiers. Great. So now let's take any one particular set. So all we need to show is that the existence of one set of size 1 which is shattered, and that, as we can see, you pick any point. If you take the hyperplane on one side, you get a 0, a hyperplane on the other side, you get a 1. The same holds true for x1, x2, right? You take any 2 points, and you can generate all 4 combinations. Either you take a hyperplane on one side, having both the points on one side of the hyperplane, or the hyperplane passing through or passing in between the 2 points, right? Something that separates the 2 points. Okay. So that's fine. But now let's go to the case m equal to 3. Right?
That particular case, you put a BC dimension one, right?
The previous example, this example.
Yeah.
Okay.
We can get all functions.
How?
Since it's real number, I'll always be able to find suppose x1 and x2 two samples I'm taking.
Okay, without loss of generality, let's assume that x1 is less than x2.
That's the case. If I choose my alpha less than x1,
Okay,
it will be 1, 1.
correct.
The alpha is between x1, get 0.
So yeah, so you can always,
You won't get 1.
you won't get 1, 0. You can generate everything else except 1, 0 in this case. Right. That's why the VC dimension happens to be equal to 1. Because no matter how you choose x1 and x2, you can never get 1, 0, assuming of course that x1 is less than x2. Okay, so let's now come to the case of the hyperplane classifier with 3 points. All right. If I have my configuration in this particular form, then is it possible to generate all combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1? Uh, 1, 1, 1, you just draw a hyperplane on one side. 0, 0, 0 or 0, 0, 1 or 1, 1, 1, you just take the hyperplane on one side. Something that does not separate these points. All right. Anything else you can, that's okay. I just need to demonstrate the existence of one subset. Right? So the VC dimension is at least 3. Right? Okay, now let's look at subsets of size 4. My claim is that the VC dimension is equal to 3, which means that I will show that no matter how I choose x1, x2, x3, x4, I will not be able to shatter this. Okay, so every set of size 4. Now, in general, this is the hard part, right? You want to show that nothing can be shattered. Question? Okay, so I essentially need to, I'll split this into 2 scenarios. All right, one is where x1, x2, x3, x4, x2, x3, x4 form a quadrilateral or a convex polygon. Right, and in the other case, they do not form a convex polygon. So the 2 scenarios are, one could be scenario like this. This is case A. And case B, where when essentially the 4th point lies within the convex hull of the other 3 points. This also includes the case for instance, when they're collinear, or let's say 3 of them are collinear and one does not lie in the straight line passing through the other 3. So just convince yourself that this handles all possible scenarios. Okay, so now let's look at case 1. What I need to show is that this set is not shattered by the hypothesis class. Is it possible to get the is it possible to draw a hyperplane so as to get the following labeling? It's impossible, right? Because no matter how I try to draw the hyperplane, I can't. Essentially, I will want to separate these 2 points and these 2 points, but have these 2 points on one side of the hyperplane, which is not possible. Right? So this set is not shattered by, or sets of this particular form are not shattered by H. What about this case? Can you give an example of a labeling which is impossible to generate using H? Yep, the ends of the triangle have one label and the one inside the triangle has a different label. This is impossible to generate using hyperplane classifier. So no set of size 4 can be shattered. Any questions? Okay. So, as I had briefly alluded to in the last class, the VC dimension essentially gives a lower bound on the sample complexity of pack learning. Okay, it's a very simple lower bound, and you can state it as follows using the no free lunch theorem. So suppose that H shatters Xn for some finite set Xn. If you observe fewer than m by 2 samples, then what does the no free lunch theorem say? It says that if the size of the set is less than m by 2, then the learning algorithm essentially can't achieve an arbitrarily small epsilon and delta. So in other words, no matter how you choose your learning algorithm, for every choice of a learning algorithm, there is some distribution and some concept, right? Remember that the concept class, when restricted to xm, should be the set of all possible functions from xm to 0, 1. So the no free lunch theorem says that no matter, for every learning algorithm, there is some bad distribution and some bad concept for which the probability that the learning algorithm, so with probability at least 1 by 7, the learning algorithm achieves a generalization error which is larger than 1/8. So if it is not pack learnable, then it is also not agnostically pack learnable. Okay? Because pack learning is a special case of agnostic pack learning. This also means that there exists a pxy for which this is greater than or equal to 1 by 8 plus r of whatever r star is greater than or equal to 1 over 7. Right. So in general, for agnostic pack learning, probability that R of HS is greater than or equal to R of H star, the best possible generalization error within the class, plus 1 by 8 is going to be greater than or equal to 1 by 7 for some pxy. This pxy could depend on the choice of the learning algorithm. So, for example, if you use ERM, then there exists one particular bad pxy, at least one bad pxy. If you choose a different learning algorithm, maybe something like ERM plus a regularization term, then maybe the bad pxy could be different. Doesn't matter, but there will be a bad pxy.
We said that there exists function of an
Correct, which is
what we mean by the snippets of
so that's effectively saying that there is some concept, right?
but that concept can be a bad classifier. Not be
The concept achieves zero generalization error, right?
but which there can be multiple.
So in the let's go back to the definition of the no free lunch theorem. Yeah. So we're assuming, of course, the no free lunch theorem, you can look at it in a slightly general way. So suppose that you always restricted yourself to a particular x, which has m elements, right? Then this particular statement essentially corresponds to there is some f from those m elements to 0, 1, which belongs to the hypothesis class. That's all that this is
But
saying.
there we are saying no x.
Correct, but this is a slightly more general scenario, right?
When it is go x by this may not be a true.
This is the true classifier, right? Because if R of f is equal to 0, what does it mean? That this is a concept, right? So in other words, y is a deterministic function of x. Only then you can achieve R of f equal to 0.
When we have rho x, R of x equal to c may not be the because y itself is a proper.
But if R of f is equal to 0, this particular statement means that y is a determinant. Okay, so over all x with positive probability, this R of f, the mapping from x to y is deterministic with probability 1, right? This happens.
And what will make us a rho x?
So again, if it makes things simpler, just assume that the statement says there exists a px and there exists an f. So the no free lunch theorem, as I said, can be generalized a fair bit. You can think of scenarios where x is not necessarily finite, and so on. There are minor variants. So if it makes things easy, you can just assume that the statement is there exists a px and a concept c in H such that this holds. That's one of the simplest ways of looking at this, and that's the only version that we will need.
X is
X is,
the domain set.
it can be infinite, but then you only restrict yourself to a H which is some set of functions over a subset of size over a smaller subset.
Then what about this cardinality?
Which the cardinality of that's finite, right?
Domain set is how
The
many
domains.
strands?
So then your hypothesis class will have a finite set of samples. So
Then the bound on the strand.
then this ultimately the bound on the training samples will depend on the bound of the hypothesis class, right? So here if you want to take x to be infinite, that's another way of stating the no-freelance theorem. If you take x to be infinite, then you will have to set things up in terms of restrictions of h to some finite set. So if the restriction of h to some finite subset of size 2m happens to be the set of all functions from this set to 0, 1. So in other words, if h shatters a set of size 2m, then this happens. There exists a distribution px for which the generalization error of any learning algorithm is large with constant probability. Is that okay? Any questions? Okay. So essentially, the no-freelance theorem says that it gives a very trivial lower bound on the sample complexity of pack learning. It says that the sample complexity must be at least the VC dimension of h divided by 2. It doesn't, in no way is this going to be tight. But what it directly tells us is that if the VC dimension of h is infinite, then the sample complexity cannot be finite, and therefore this particular hypothesis class is not pack learning. And if it is not pack learnable, it's also not agnostically pack. All right, great. Now, related to the VC dimension, there's also this notion of a growth function that we'll also use in a little while. So the growth function, so for any m, right, what you want to find is, if I look at the restriction of h to this particular set of to any set of size xm, then what is the size of the largest restriction of h to xm over all subsets of size m? Right? So this is a function of m. Right? So it gives the size of the largest restriction of h to subsets of size m. For what m? So if m is less than or equal to d, so suppose that the VC dimension of your hypothesis class happen to be equal to d, right? What would be, what can you say about the growth function for m less than or equal to d? It's going to be 2 to the power m, right? Because there exists at least one set of size m which is shattered by h, and therefore this, and you're taking the maximum over all possible m. So it should be 2 to the power m. What can you say about m greater than d? Something which is strictly less than 2 to the power m, but you can't conclude anything beyond that. Right? So basically the VC dimension is this threshold for the growth function. Up to d, the growth function grows exponentially at this particular rate, but beyond that, at least the rate changes. This is for restrictions, yes. We're restricting to subsets of size m. And we're looking at sort of largest restrictions over subsets of size m. Okay. And at the end of last class, I had introduced this fundamental theorem of pack learning for binary classification, which had a bunch of conditions which happen to be equivalent. So if your hypothesis class satisfies the uniform convergence property, then it's pack learnable and it must have finite VC dimension, and ERM is always going to be an agnostic pack learner for H. So some takeaways from this fundamental theorem of pack learning is that if you're doing binary classification, then you know which algorithm you have to pick. You just pick ERM because it is going to be an agnostic pack learner. You don't have to worry. It may not achieve the best sample complexity, but doesn't matter, it's still going to do reasonably well. All right? And in the case of in the special case of binary classification, pack learnability is equivalent to agnostic pack learnability. Right? Question? By good agnostic pack learner, I mean that it achieves a sample complexity that is going to, or the number of samples that you require to achieve an epsilon delta error is going to be pretty close to the sample complexity at all. So if there is, so in other words, the number of samples required by ERM to achieve some particular epsilon and delta are close to what the best possible learner can, the number of samples that the best possible learner requires to achieve the same epsilon and delta. They could be off by a factor of a few constants, but that's about it.
But H star,
I'm sorry?
it should be close to what H star.
With the best algorithm, learning algorithm.
If 4 is true, 6 is true.
If 4 is true, then yeah, 6 is true. Correct.
No, but when we are proving, we need to prove something for making it all the plus. Correct. You have to, that 4 should imply something. Right?
Which one?
There is no arrow.
Okay, sorry, yeah. So, I mean, a lot of things go into 6. So, of course, 4 implies 6. 5 also implies 6. 3 also implies 6, and 2 also implies. So all of these, if any one of these is true, then 6 has to be true. So to prove that all of these are equivalent, we still have to prove that 6 implies 1. That's the only missing link. Correct. Correct.
So we did that ERM was good agnostic pack.
We did. That's true. So, and that's not something we will prove here. All right. Because for that, you will also need to prove a lower bound, that so first you'll need to show that as long as m is greater than a certain amount, so in fact let me state that. So what one can show is the following. One can show that if the VC dimension is equal to of the hypothesis class is equal to D, then you can prove that the sample complexity is upper bounded by some constant times D plus log 1 over epsilon, log 1 over delta divided by epsilon for agnostic pack learning. Epsilon square for agnostic pack learning, and it's lower bounded by some other constant C1 times D plus log 1 over delta divided by epsilon square. So we will show that this is true, that the sample complexity is at most C times D plus log 1 over epsilon divided log 1 over delta divided by epsilon square, and this is achieved by ERM. Okay, to show that this performs close to the best, you also need to prove an appropriate lower bound, which you will not do in this particular course, but that's something that you can prove. You can show that no matter what you do, the best possible learner has to take at least these many samples in order to achieve an epsilon and delta error. So this is true for agnostic pack learning, but if you knew that h was equal to the concept class, then you can shave off another factor of epsilon, and this is just D plus log 1 over delta divided by epsilon. As you would expect, if you are trying to perform agnostic pack learning, then you would require more samples. Epsilon is less than 1. So this quantity is larger than this particular quantity. Right? But again, I'd like to point out that all of these statements hold true only for binary classification. Right? Even if you go to regression, this statement is not true. But all of these equivalences are not true in general. Okay, so in trying to prove that 6 implies 1, we'll rather go through a long route. Right? I'll introduce another notion of complexity of a particular hypothesis class. So the VC dimension was in some sense one measure of complexity of a hypothesis class, but now we'll see another measure of complexity, and we'll see, when we show that if you have that these two are related. So in other words, we'll bound our general approach will be the following. We'll show that the generalization error of ERM can be upper bounded by this some function of this Rademacher complexity that I'll introduce next. And then we'll show that the Rademacher complexity is in turn can be upper bounded by the growth function. And we'll show that the growth function can then be upper bounded by some function of the VC dimension of the hypothesis class. So these are all related notions, and some of them are more easier to compute than others. So the Rademacher complexity is in general hard to compute, whereas the VC dimension, at least for certain simple cases, we could really compute and find out what the VC dimension was. Okay, so what is the Rademacher complexity? So to define this, we'll look at a slightly different representation of the loss function, and, or in other words, another representation of the hypothesis. So I'll define, so for a given H, we'll define G to be set of all G of x comma y. So this is again a collection of functions, and the function takes two inputs, one an element from the domain and a label, and this is just equal to the loss achieved by a particular hypothesis on this particular sample x comma y. The collection of all such G's is what constitutes this set script G. Okay. So in other words, these are all possible choices that the loss function can take in some sense. Right? And this holds true irrespective of what loss function I pick. Okay. So using this, I'll define the empirical Rademacher complexity. I'll denote this by RC subscript S. So for a given G, for a given function G, and for a particular training sample S, the empirical Rademacher complexity is just 1 over n summation I equal to 1 to n G of xi yi, but now this is going to be multiplied with a sigma I, and I'll take an expectation with respect to sigma. Alright, it's a weird looking function where this sigma, these sigma i's are going to be IID Rademacher random variables. So in other words, they take two values, so each sigma I can take either +1 or -1, and they take these values with equal probability. Sigma I is equal to 1 or -1, and this happens with probability half. Correct. Rademacher random variable is just a transformation of an IID Bernoulli half random variable. Yeah.
Defining that g of x equals to L of x.
It's L of h of x comma y, right? Because the loss function, so this is the prediction that is made by h, and this is the true label. Sorry?
Sigma I is also from.
So sigma i's are generated independently. Okay. They're completely independent of, so this is for a given training set. Right? For a given training set, I define this empirical Rademacher complexity. Just take n pairs of x comma y and you compute this quantity. Right now, there's no real intuition as to why I'm defining this. Okay. Something I'm just defining. And the Rademacher complexity is going to be just the expectation of this with respect to the samples. Because in the right now, there's still some more randomness in left over in x comma y. The training set, this depends on the training set. Also, something. So let me correct. I should also take a supremum with respect to G in G. This is for a given set. Sorry about that. Right, so what do? I take out of this particular average. Now this quantity is a random variable that depends on xi, yi, and sigma. All right. Among all of these, I maximize overall possible G. G can be thought of as, okay, so without the sigma, right, this would just be the empirical risk. Right? But I'm just introducing this sigma I artificially. So it's not really the empirical risk, but I'm also randomly subtracting some of the losses. Right? So just to be clear, just 1 second. Rs of h is nothing but 1 over n summation I equal to 1 to n G of xi yi. All right. And also another point is that the minimum empirical risk is equal to the infimum of this, or the negative of the minimum empirical risk is equal to the supremum overall G in G of 1 over n summation I equal to 1 to n minus 1 times G of xi yi. Right, so just some observations over here. There's a question?
The expectation.
Correct.
Body action.
So this is supremum over functions, right? So for each function g, I get, so let's fix sigma, let's fix x, fix y, right? So
sigma as in we are drawing a sample.
we're drawing a set of samples, right? We're drawing samples sigma, randomly drawing samples sigma. Again, this is for a given training set.
But can't it actually change in sigma?
Which one?
The corresponding supremum.
Correct. The supremum, of course, depends on sigma. That is true, right? So for each choice of sigma, so each configuration of sigma, you have a different supremum. No doubt.
So how do we work out that? I feel like it's a circle, and like a circular dependence.
Why is it a circular
Only
dependence?
if I fix sigma I, I'll be getting the supremum. The moment I fix a sigma I, won't become a RV anymore.
For every sigma, I get a different supremum, right?
Yeah.
So let's just take let's take a very simple case of n equal to 1. Okay, trivial case of n equal to 1, just one sample. Then what does the Rademacher complexity correspond to, or the empirical Rademacher complexity correspond to? Of g, this would be, okay, now how many choices of sigma do you have? 2, right? So sigma can take either +1 or -1, right? So sigma can take 2 different values, +1 and -1. So what would that be? I would get n is 1, so supremum over all g in g. Now g could be an infinite set for all I know, of this particular function that I have over here, which is g of xi yi plus supremum over all g in g -1 times g of xi yi, right? So that would be the supremum minus the infimum of g of xi yi in this special case.
1/2 prior.
Correct. So there's a 1/2 prior as well. So times half. So this would be half of supremum over g of xi yi minus the infimum over g of xi yi. If n is equal to 2, now there'll be 4 different configurations for sigma. For each configuration, you can compute the supremum, right? And
okay, that will be an expectation vector.
correct. So expectation is just a summation, right? In this case, everything is discrete and nice. So it's well defined. You're right, computing this is going to be very, very hard, right? Because of course we're interested in the regime where n is large, which means that for sigma there are 2 to the n possible configurations, and for each configuration the supremum could be different. So computing this is not easy, but it's well defined. That's all that we care about. That's why finding the Rademacher complexity is hard. The VC dimension, on the other hand, is something that is easier to compute in most situations. So this is the Rademacher complexity for a given sample. So what is the Rademacher complexity? I'll use the notation RC subscript n of g because it depends on the number of samples. So this is expectation, assuming that the ground truth is drawn according to the distribution pxy of RCS, where these n samples, the training set, is drawn IID according to PXY G.
Expected over all the possible.
Yeah, so you take the expectation with respect to the training set. Yeah.
N has nothing to do with the total number of samples.
No, n is the number of samples that you have. So this is the size of the training set. Yeah, that's exactly why I've kept there. So the Rademacher complexity depends on of course the hypothesis class. It depends on the number of training samples that you have, and it also depends on PXY. Fixed size of the range. Yes. Assuming that I have n samples to work with. Okay. So why is the Rademacher complexity useful? It's useful because of the following statement that we can make. So I look at a slightly more general setting beyond just binary classification, because all of these definitions at least make sense irrespective of what the loss function is. So let L be any loss function that is bounded between 0 and 1. Right? This bound can be arbitrary, but I'm just fixing it to be 0 and 1 so that I don't have any other unnecessary constants. Okay. Then with probability at least 1 minus delta. Of course, this is over the training set S. The following happens for all H. The generalization error for all H are going to be in some sense close to the empirical risk. So this is nothing but the empirical risk plus a term which is just 2 times the Rademacher complexity of G plus square root of log 1 over delta divided by 2 times n. So if the Rademacher complexity of G is something that decays roughly as 1 over 2n, right? For all, so if it is roughly 1 over 2n, then the generalization error is going to be very close to the empirical risk for all H in the hypothesis class, and I'll have uniform convergence. I can also show plus 2 times the empirical Rademacher complexity plus something that's a little larger, 3 times square root log 2 over delta divided by 2n. Right, so if this quantity decays as, let's say, order 1 over square root 2n, then we'll get uniform convergence. Or if this is, say, some constant times this, then we get uniform convergence. Because it means that with high probability, the empirical risk, the generalization error is actually very close to the empirical risk for all hypotheses in the hypothesis class. I'm sorry? That's even stronger, right? So, in fact, as long as it is, ultimately what we will show is that it's square root log 1 over delta divided by n. Because this is larger than just order 1 over square root.
Normal Rademacher.
Sure, I mean, some cases you want the, it depends. More often than not, we will use this particular bound. Yeah, they're anyway hard to compute. Both of them are hard to compute. But this is also telling you something more. In fact, the way we will show the second statement is by showing that the empirical Rademacher complexity is also very close to the actual Rademacher complexity with high probability. All right. And yeah. Correct. Then it is pack-learnable, yes. Right. So this gives a direct connection between the Rademacher complexity and uniform convergence, and hence pack-learnability. So if I am somehow able to connect the VC dimension with Rademacher complexity, then I'm done. But first, I'll of course need to show that this statement is true. Right? That the Rademacher complexity essentially gives me a tight bound on the generalization error. Which one? So suppose that this holds, right? Okay.
long as our CN is decaying,
Huh?
we could make sure that the empirical error is more CN.
It could, but also it'll kind of give me something like this. I'm not just interested in the fact that it is pack learnable, but I also want a handle on the sample complexity itself. So if I get a loose bound on that, then I don't get a tight bound on the sample complexity. That's the only reason. So effectively, all I require for pack learnability is that this Rademacher complexity is decay with n. That's enough. You're right. So let's see how this particular bound would be helpful. So if the Rademacher complexity is some constant times square root log 1 over delta by n, then this overall term would be constant times square root log 1 over delta by n, right? Then I would be able to say so suppose that the Rademacher complexity is order square root log 1 over delta by n, then effectively what the theorem says is that the probability that, let me take the positive statement, for all h in h, r of h is less than or equal to rs of h plus some constant times square root log 1 over delta by n. This probability is at least 1 minus delta. Correct? So ultimately I want to achieve an error of at most epsilon. So let me take this term to be equal to epsilon. Okay. So what does that tell me about the n? So c times square root log 1 over delta by n is equal to epsilon, which implies that if I square both sides and rearrange, I'll just get n to be equal to it's 1 over epsilon square, or c by epsilon square log 1 over delta. Right? So that will give me sort of the correct behavior. In fact, suppose that this, even otherwise, we can still get a bound on the sample complexity, right? So if I take this whole quantity to be equal to epsilon, right, then what is n? What is the sample complexity going to be equal to? So I have 2 times the Rademacher complexity of G plus square root log 1 over delta divided by epsilon to be equal to, I'm sorry, divided by 2n to be equal to epsilon. One over delta divided by 2n. This is equal to epsilon minus 2 times the Rademacher complexity the whole squared, or n is equal to log 1 over delta divided by epsilon minus 2 times the Rademacher complexity of G of the whole square.
You can't solve.
I'm sorry?
You can't solve.
Why can't I solve?
RCA.
Correct, you're right. So suppose that the Rademacher complexity were something that, let's say, decayed as 1 over n, right? Or suppose that the Rademacher complexity were bounded. So in scenarios where I can bound the Rademacher complexity, I can get a bound on the sample complexity. But yeah, you're correct that I can't in general make a claim on the n because the Rademacher complexity also depends on it. Okay, any questions? Okay, maybe this is a good point to stop. In the next class, I'll prove this particular theorem, and then we'll proceed to see how we can bound the Rademacher complexity in terms of the growth function and the growth function in terms of the VC dimension.